In this video, I will talk about dynamic inefficiency, what it is, and whether it can occur in the models of Solow, Ramsey-Cass Koopmans, and Diamond, the overlapping generations model. Now we know from the Solow model that output per unit of effective labor always increases with the saving rate. But we also know that in general, individuals are not only interested in income. What matters in their utility function is consumption, again, per unit of effective labor. In the following, I will leave aside per unit of effective labor in the slides particularly. But what's important is that everything that holds for consumption per unit of effective labor also holds for consumption per capita, only with the difference that consumption per capita additionally follows the long-run growth trend at the rate of technological progress. Now, the next figures show how consumption behaves in the Solow model when the saving rate increases. So this figure shows the standard Solow diagram where we have output per unit of effective labor, lowercase y tilde on the vertical axis, and capital per unit of effective labor, k tilde on the horizontal axis. We have the concave function of output per unit of effective labor depending on capital per unit of effective labor that follows from the Cobb-Douglas production function. And we have the linear capital depreciation and capital dilution line. Now, for a low saving rate, say S1, we have an intersection between the gross investment curve, so that's invested, and capital depreciation and dilution at a comparatively low level of capital per unit of effective labor. And we can read off consumption per unit of effective labor at the steady state as the difference between the two curves, the output and gross investment. Now, if we increase the saving rate, say to a higher level, S2, we would have an intersection between the gross investment curve and the capital depreciation and dilution line at a higher level of the capital stock per unit of effective labor. And correspondingly, we would here have a higher consumption per unit of effective labor. However, if we increase the saving rate further to S3, then we see that output per unit of effective labor and capital per unit of effective labor at the steady state increase further, but consumption per unit of effective labor now decreases as compared to the situation with the lower saving rate. So this makes clear that consumption per unit of effective labor at the steady state does not necessarily increase with the saving rate. If we start from low saving rates, consumption would increase with an increasing saving rate, but at some point the additional effect becomes negative. And this is a consequence of the concavity of the production function, which is the case in case of the Cobb-Douglas production function, and the linearity of the capital depreciation and dilution curve. So each additional unit of output that can be generated by an additional unit of capital decreases due to the concavity of the production function, while depreciation and dilution increase linearly. And that means that at some point onwards, it will definitely be the case that the additional output that can be produced by increasing the saving rate is more than offset by the additional depreciation and dilution. Now, two things are obvious, and that's that for a saving rate of that is equal to 0, nothing can be consumed at all because nothing can be produced according to the Cobb-Douglas production function. And on the other hand, with a saving rate of 1, it's also the case that nothing can be consumed because I save everything. So everything I do is to try to accumulate capital just to be able to compensate for capital depreciation and capital dilution. And somewhere in between these two must then be a saving rate that maximizes consumption per unit of effective labor at the steady state. And this level of the saving rate is called the golden rule saving rate. This is illustrated graphically here, where we have consumption per unit of effective labor on the vertical axis and the saving rate on the horizontal axis. Now, initially, for a low saving rate, output per unit of effective labor would increase quite strongly for an increase in the saving rate. And the increase in output will definitely be higher than the increase in capital depreciation and capital dilution, so that more additional output can be produced. And this can also be consumed. So consumption will definitely increase with the saving rate here. However, if we are here at the saving rate of 1, we cannot consume anything because we save everything that we have, basically. And somewhere in between would be the saving rate that maximizes consumption per unit of effective labor. And in this case, this would be here, and the corresponding saving rate would be the golden rule saving rate that maximizes consumption per unit of effective labor at the steady state. The reason that this definitely looks like it is drawn here is that the that the production function is concave, and the depreciation and dilution line is linear, which means that the first additional unit of additional capital increases output quite strongly. So recall the another condition. So the increase here is quite strong. But then it flattens off and flattens off, and at some point, the additional output generated by additional capital is exactly as high to offset the additional depreciation and additional capital dilution when the two lines are parallel. But then, from this point onwards, the additional capital depreciation and capital dilution is even higher than additional production, and consumption per unit of effective labor would decrease again. So now we know that the saving rate can be too high when the aim is to maximize consumption at the steady state. But what about the transition period? So actually, if we want to make general statements for the transition period and the steady state, we also need to know what happens during the transition period. Now, if we increase the saving rate from a level below the golden rule saving rate to a rate that is still below the golden rule saving rate, then we have that in the short run, consumption per unit of effective labor decreases. That's clear, because increasing the saving rate means I consume less. I sacrifice short run consumption. But then capital accumulation sets in. This raises the capital stock, it raises production, it raises income, and it raises consumption. And if I'm still below the golden rule saving rate, then what I definitely would have is that the steady state level of consumption would be higher than the initial level of consumption. So a short run sacrifice in consumption due to the higher saving rate would lead to a long run gain, a higher steady state consumption level. But if the economy starts with a saving rate that is already above the golden rule level, then an increase in the saving rate would mean a short run sacrifice of consumption. But due to the fact of what we've just analyzed, that also the steady state consumption level decreases, we would have that not only short run consumption decreases, but also long run consumption decreases. And that's clearly, for a rational agent, it would not be optimal to do this. So it's inefficient actually. And this is called dynamic inefficiency, that I have a saving rate that is so high that a decrease in the saving rate actually can make everybody better off, because the cohorts in the short run would benefit because the saving rate would be reduced so they can consume more, but even the steady state consumption would be higher because of what we've just seen. This is now further illustrated in the next two figures, where we have consumption per unit of effective labor on the vertical axis and time on the horizontal axis. We assume that we start in the steady state, so consumption per unit of effective labor is constant, but then at some point t hat, the saving rate increases from S to S prime. Now this is the case of a dynamically efficient economy. When the saving rate increases, I make a sacrifice in short-run consumption in order to be able to consume more in the long run. So I would have a typical intertemporal trade-off. I sacrifice consumption and utility in the short run, but I gain in the long run. However, if we start from a saving rate that is already higher than the golden rule saving rate, then what we would observe is the following. Again, we have consumption per unit of effective labor on the vertical axis, time on the horizontal axis. And now at time t hat, again, the saving rate increases from S to S prime. We see again the short run sacrifice in consumption, but we see that the long run gain that we then have is way below actually of what we could have consumed initially. So actually we don't only have a short run sacrifice, we also have a sacrifice in the steady state. So we have that every generation is made worse off by the increase in the saving rate. And by implication, that means every generation can benefit by decreasing the saving rate. And that's what dynamic inefficiency is all about. Now let's go a little bit more into the mathematical details. what would be the saving rate that maximizes consumption per capita at the steady state, C star. So this can be computed by maximizing C star by choosing the saving rate S, and consumption is given by 1 minus the saving rate times output per capita. So that's by definition, everything that I do not consume, I save. So consumption is 1 minus savings, and that's what we've here. Then I can plug in, instead of output per capita, output per unit of effective labor multiplied by technology. So that's the same as output per capita. And then I plug in the production function here. So the Cobb-Douglas production function in efficiency units, it's K star tilde to the power of alpha. Now at the steady state, we know that gross investment, which is the saving rate multiplied by output per unit of effective labor, minus capital depreciation and capital dilution is equal to 0. That's the definition of the steady state. So we can use it in the following derivations, where we have here just the reformulation here. We multiply this out and therefore have this term here, and this term here is minus S times this, and we can bring A in front of the squared brackets. And then we substitute out for S, K tilde to the power of alpha, the N plus G plus delta K tilde. So we just substitute this in. And then we want to maximize this consumption per capita. So what we do is to compute the first order necessary conditions for such a maximum. And that's that the derivative of consumption per capita with respect to the saving rate has to be equal to 0. So the derivative of this right-hand side expression has to be equal to 0. Now we see so A drops out because it appears in both terms, so we can just cancel it. We take the derivative of this term here with respect to the saving rate. So that's the outer derivative by the chain rule. Alpha comes down from the exponent, and the exponent is reduced by -1. And we have the inner derivative because K tilde also depends on the saving rate. And that's written outside here because we also have a K tilde here, so we can multiply the two terms. And then if we take the derivative of the second term with respect to the saving rate, we see that this is this term here that multiplies with capital per unit of effective labor, that remains by taking the derivative, and then we have the inner derivative of K tilde with respect to S, the same expression that we had here, so we can put this in front of the squared brackets. That has to be equal to 0 for an internal maximum. Now on the previous slide that we had, we know that the expression here, the derivative of the capital stock per unit of effective labor at the steady state with respect to the saving rate is positive, because in the Solow model it's always the case that the capital stock increases with the saving rate at the steady state. So this term here is positive. So for this to be equal to 0, we must have that the term in square brackets is equal to 0, which means that this expression here is equal to this expression here. So that we have here, and here we can plug in for this term here, which is the marginal product of capital per unit of effective labor, the gross interest rate. So that's the interest rate, the net interest rate, plus the rate of depreciation. Now we see the rate of depreciation appears on the left-hand side and the right-hand side, so it drops out, and we have that the net interest rate must be equal to the rate of population growth plus the rate of technological progress. In this case, the economy would attain the golden rule saving rate and would therefore maximize its consumption per unit of effective labor at the steady state. So this condition would hold if the economy attained the golden rule saving rate. But what is the golden rule saving rate as such, so that we cannot yet say directly from this equation? So what we do is we plug back in for the gross interest rate, the marginal product of capital. So we are in the first expression again. Then we multiply both sides by capital per unit of effective labor at the steady state. So we have here that the exponent is, so this -1 drops out. And here we have the right-hand side multiplied by K tilde star. Then we use what we had on the previous slide, that at the steady state, the saving rate multiplied by output per unit of effective labor would be equal to gross investment, and that's equal to the rate, the total capital depreciation and capital dilution. So we can plug in here the saving rate on the right-hand side multiplied by output per unit of effective labor at the steady state. And on the left-hand side, we see that we can also plug this expression in here on the left-hand side. And we see that actually, so that's output per unit of effective labor here, what we can plug in. And then we see that we have actually alpha times output per unit of effective labor on the left-hand side. And on the right-hand side, we have the golden rule saving rate multiplied by output per unit of effective labor. And that implies immediately that the golden rule saving rate is equal to alpha. And that means nothing else than that the economy should save all its capital income and consume all its wage income. And then it would be at the golden rule saving rate in the Solow model. So the golden rule saving rate in the Solow model would be equal to alpha. So now we know what the golden rule saving rate is in the Solow model, and we know that dynamic inefficiency can occur in the Solow model. And the reason for that is basically that there are no rational agents in the model that would consider that their increase in the saving would have effects on the interest rate of the cohorts that follow. So it would have an effect on the interest rate in the future. So nothing prevents agents actually from having a very high saving rate. The saving rate is a parameter, and it could be inefficiently high, therefore. However, how does it look like in the Ramsey-Cass Koopmans model or in the diamond model where we have optimizing agents? And that's what we will look at next. So first we look at the Ramsey-Cass Koopmans model. And here we know that steady state consumption per unit of effective labor follows from the K tilde dot zero isocline, where we have that consumption per unit of effective labor then is the difference between production per unit of effective labor and capital depreciation and capital dilution. So if we want to maximize consumption per unit of effective labor again with respect to the capital stock, we would need to take the derivative of this expression with respect to K tilde and set it equal to 0, and that means basically we have the derivative of the production function with respect to capital per unit of effective labor at the golden rule level of the capital stock. So that's the marginal product of capital again. And on the right hand side, this drops out, so we have n plus g plus delta. And now we know again that the left-hand side is equal to the marginal product of capital. So that's the gross interest rate. So that's the interest rate plus the rate of depreciation. We also have the rate of depreciation on the right-hand side. So again, we would get the condition that for the golden rule capital stock, we would have that the interest rate must be equal to the rate of population growth plus the rate of technological progress. So it's the same as in the Solow model. However, in the Ramsey-Cass Koopmans model, the transversality condition has to hold. So the product between the capital stock per unit of effective labor and effective discounting as time goes to infinity must be equal to 0. And that means that this term in the exponent of E must be negative because the capital stock increases and capital accumulates. Now we have a negative sign here, so that implies that the term in squared brackets must be positive. And the term in squared brackets is the marginal product of capital, and it has to exceed the marginal product of capital minus the rate of depreciation, which is the interest rate, has to exceed the rate of population growth plus the rate of technological progress. So we must have that the interest rate in the Ramsey-Cass Koopmans model is greater than the population growth rate and the rate of technological progress. And this in turn implies that the capital stock per unit of effective labor at the steady state will always be lower than the golden rule capital stock per unit of effective labor because the marginal product of capital is higher than n plus g. And this rules out dynamic inefficiency in the Ramsey-Cass Koopmans model. This can be shown graphically by our two isoclines, the C tilde dot 0 isocline and the K tilde dot 0 isocline, where we've said already that the C tilde dot 0 isocline always intersects with the K tilde dot 0 isocline to the left of the maximum of the K tilde dot 0 isocline, and that's a consequence of what we've just discussed. So we will always have the steady state here at the capital stock per unit of effective labor that is lower than the capital stock per unit of effective labor that maximizes the K hat dot zero isocline. So that would maximize consumption per unit of effective labor. Now, what's the intuition behind that? The intuition is simply that we have rational agents with perfect foresight and perfect altruism in the Ramsey-Cass Koopmans model. So when they maximize their utility, they take into account that if they increase their savings, that will have an effect on the saving rate of future cohorts. And by taking this into account, they internalize this dynamic inefficiency, and dynamic inefficiency cannot occur due to the fact that individuals behave optimally and are perfectly altruistic towards their children. Now, finally, in the overlapping generations model of Diamond, dynamic inefficiency can again occur at the steady state, irrespective of the fact that we have optimizing agents. To show this, we start with output that can be consumed or saved. So we have output as a function of capital input. Now we have everything per worker because in the basic OLG model we abstracted from technological progress. And total output is either used for saving or for consumption. And consumption refers to both generations, the one that is young and the one that is old. So basically consumption at the steady state is made up of consumption of the young and consumption of the old. And here we have to adjust for population growth because those who are old today, this cohort was of size 1 over 1 plus n the period before. Savings are equal to 1 plus n times the capital stock. And we can then rewrite consumption per worker at the steady state as output minus 1 plus population growth times capital. Now, the golden rule, capital labor ratio or capital per worker, can then be derived again by taking the derivative of this expression with respect to K star at the steady state. And we see that this is the derivative of the production function here with respect to capital. And here capital at the steady state drops out. So we have minus 1 plus n, and this has to be equal to 0. Then we again know that this is the marginal product of capital. So we have uppercase R here, so the gross interest rate. And that has to be equal to 1 plus the population growth rate for the capital stock at the steady state that is equal to the golden rule. Now, however, in the overlapping generations model, nothing prevents actually the gross interest rate from being lower than 1 plus n, and therefore the net interest rate to be lower than the population growth rate because the rate of depreciation is equal to 1 in the standard overlapping generations framework, because over one generation the whole capital stock depreciates. And that means that actually there is no restriction in the overlapping generations model why dynamic inefficiency could not occur. And the intuition behind this result is that there is a lack of intergenerational altruism in the basic OLG model. So people save for retirement, and there is a strong incentive to save for retirement. You don't have an income when you are old, and therefore you try to do everything for your consumption smoothing actually and save a lot, and not considering actually which impact this has on the interest rate of following generations. So that's the intuition why dynamic inefficiency again can occur in the overlapping generations model. So now we can summarize our observations with respect to dynamic inefficiency. We've seen it's possible that economies are dynamically inefficient, and the Pareto improvement is actually possible by reducing the saving rate if the saving rate is very high. Theoretically, dynamic inefficiency can occur in the Solow model because of a lack of rational agents. So the saving rate could be 1, which is clearly irrational, but it would be possible in the model. So nothing prevents the saving rate from being so high. And it can occur in the overlapping generations model, although there are rational individuals making the decisions, but there it could occur because of the lack of intergenerational altruism, that people don't care for the next generation and that an increase in capital decreases the interest rate for the next generation. However, dynamic inefficiency cannot occur in the Ramsey-Cass Koopmans model, and that's because there are rational agents and they combine with perfect intergenerational altruism. So The optimizing agents care about their offspring and take into account that if they increase their savings, then future generations would not earn that much capital income. Now the question looms how relevant dynamic inefficiency is in reality. And there, it's typically the case that empirical findings suggest that saving rates are not high enough to be in the dynamically inefficient territory. Japan in the 1980s and China in the 2000s and beginning 2010s had very high saving rates. So there it was a little bit debate going on whether this is already dynamically inefficient. But by and large, I think people agreed on that it's not a huge concern yet. Nevertheless, China, particularly over the last decade or so, tried to rebalance its economy in the sense of increasing domestic consumption, and that means decreasing the saving rate. And perhaps one of the reasons for that was a concern about dynamic inefficiency.